So module 4 is customizing the search method of AutoML in continuation from the last class. That is sampling the new hyperparameters via the acquisition function. And so it is like what is in this particular topic, the problem with the dump search and scenario. Like imagine you're trying to find the highest point in a vast foggy mountain range, example the lost landscape or something like that. You can only check your altitude, the validation loss by hiking to a specific location, training a model with a specific hyperparameter set. It is similar to that. Each hike takes 8 hours and cost is $100, something like that. So in the grid search, like checking a predefined grid of a location on your map, you might miss the peak entirely if it's between grid points. Very wasteful. Like means they're trying in a grid search method. So you'll be searching grid by grid. So if you want to search particular in an image, you take the particular details will be there in one place of the grid, but you will be scanning or searching all over the whole image, the grids all over the whole image, and in that doing so, you might miss that particular grid points where you have to extract the details. So that is what you might miss the peak entirely if it's between grid points. And random search is something like throwing dots at the map blindfolded, better than grid search, or but still inefficient. Like you have no memory or a strategy. So that is one drawback of the random search. Here comes the next thing is why or how. How can we use the information from the places we have already been to intelligently decide where to go next or something like that. So here the concept is based on the Bayesian optimization as a smart scout. Uh, so in this, BO has two key components, which is probabilistic surrogate model, and another one is acquisition function, which we saw the both things last. So I will just recap it. So what is probabilistic surrogate model? This is your map making tool or something like that, similar to that. And after each hike, say for example, you update your best guess of the entire mountain range or something like that. So you in the map, which is divided into several grids. Once you visit a particular grid or the area, so you will compare it with the map you have, and you will try to analyze what is the peak point when you visit that particular place in the grid of the map or something like that. The most common model is the Gaussian process. So it doesn't just give a single predictions. So what happens is it gives a probability distribution. So you have a various data points or something like that, where you will have a mean and an uncertainty or less standard deviations. With this, you can make a probability distribution. Definite probability distribution function, and you can find the outcome or what it will be, like that. And visual aid. So in this probabilistic surrogate model, the visual aid is something like show a graph with the data points, a mean function, snaking through them, or something like that, and a confidence interval that is tight near known points and wide in an unexplored regions. So next is a acquisition function. In this, it is a decision making tool. The acquisition function is a decision making tool. It uses a surrogate model maps to suggest the single most promising next location to hike to. So it helps to make a decision with the surrogate models map, and it is helping you to achieve the next hike points or make a decision to move to the next hike points or to visit or do continue the hiking. So in this AutoML loop, what you can see is build or train a surrogate model, the map based on an all hyperparameters tried so far and their resulting performances with that, and find the hyperparameters that maximize the acquisition function. And next is evaluate the actual objective function, that is train the real ML model at those hyperparameters with the hyperparameters whatever you have tuned, and add the new hyperparameters or performances paired to the history. So like as we go, this thing is to improvise the model from the history of its learning. So the model will improvise itself. So repeat until time or budget is exhausted. So that is one final things for any kind of the projects you do with the AutoML models. Next is deep dive, like what is it, the acquisition function. So these are the things which we'll be covering in detail. Uh, the where to go next engine or something like that. So we move on to the common acquisition functions like probability of improvement (PA). So idea, what is this basic idea is all about? Like what is the probability that this new point will be better than the current best point or something like that? That is defined by F or something like that. The behavior, the very greedy or something like that, tends to exploit heavily and can get stuck in local optima, not commonly used in practice anymore. We'll go to the analogy. So, what is analogy? Like, let's only go to the spots that have a high chance of being slightly better than our current best camp or something like that. So, that is what the things happen during the hiking. So, you want to camp at a better place than the previously visited places or something like that. So we'll get a better experiences. So expected improvement is the one, the gold standard. So what is this expected improvement is all about? Like it is not just about the chance of improvement, but also the magnitude of the potential improvement. What kind of impact it is going to create? The kind that kind of potential improvement is all about the expected improvement. What is the expected value of how much better it will be? So the basic behavior of this particular expected improvement is something like excellent balance. It will explore an uncertain region if the potential payoff is high enough, even if the probability is moderate. This is the most widely used acquisition function. Analogy like that for away ridge is a bit of a gamble or something like that. So what is it? But if it is higher, or it would be a huge win. Let's calculate the average payoff we can expect. So there is a formula for this, the conceptual formula for the expected improvement, EA of X. So since it is a probability, so you have a EA of X. That is probability it's better. How much better it's expected to be. That is the main thing. And upper confidence bound used to be GP or UCB, like confidence bound or head bound or something like that. Idea very explicit trade-off UCB of X equal to micro of uh, micro of X minus K sigma of X dash. So sigma of X, not of X dash, sigma of X. So what is mu X is mean prediction with the expectation term, and what is sigma of X? Uncertainty exploration terms. What is K? Knob to control the trade-off. A low K is exploitative. A high K is exploratory. Behavior is like how it behaves, intuitive and tunable, and it directly optimists an optimistic estimate of the function. Analogy, like my map says, like this spot is probably at 100 meter or something like that. What happens is, but it could be as high as 150 meter, if possible, and like being optimistic, like we have to assume it's 150 meter and we have to go there. So what is the visual demo or related to this upper confidence zone, like highly recommended to show an animation or a series of plots where the acquisition function peaks in different areas, example on a region of high uncertainty after an exploit steps or something like that. So next is with the sampling or maximization step. In this, like clarify the terminology. What is it? Sampling. So sampling. What is sampling? Like sampling is here doesn't mean the random. It means selecting or choosing the next point. The process is next hyperparameters is equal to or max of acquisition function of x. This is an optimization problem in itself. It is much cheaper because I'm sorry. So this is an optimization problem in itself, but it's much cheaper because evaluating the acquisition function only requires querying the surrogate model, not training the real ML model. So this is one advantage over the acquisition function. Like it is just querying a surrogate model, so you're not going to invest much on the optimizing the ML model over here, the acquisition function. Like we typically use fast optimizers like LBFGS or a few rounds of random restarts to find the maximum of the acquisition function. So, to recap, so what we have discussed over here is like why the hyperparameter optimization is expensive. We need to be smart with our trials because tuning, fine tuning, trying out. So it is a trial and error basis. So it takes huge amount of data sets or huge amount of memory processing time, and the cost of the infrastructure devices involved in it. So how we can perform this sampling? It is via the Bayesian optimization. Uses a surrogate model to build a proxy of the lost landscape or something like that. So what is the main function we use like key player? The acquisition function uses this surrogate model to decide the next hyperparameters by balancing exploitation and exploration. That is the main thing. Common choices like expected improvements is the most popular due to its great balance. So that is the main motto to choose the expected improvement. So these are all activities and further readings you can use these links to visual guide or you can refer the libraries. So next topic is tuning the GBDT model with the Bayesian optimization. What is GBDT? That is gradient boosted decision trees. So it is like Bayesian optimization for gradient boosted decision trees. Uh, So here, what we are going to do is identify the most critical hyperparameters to tune for the GBDT gradient boosted Bayesian tree model and understand their impacts. And next is why Bayesian optimization is particularly well suited for the tuning GBDT model, well compared to the similar methods will be discussed here. And next is to we are after once we discuss and understand. Next is to we have to prepare a step-by-step process of integrating the GBDT model into the Bayesian optimization loop. So I will show the code for the same and implement a basic GBDT tuning procedure using a VO library like Sky, Kit, Optimize, or Optuna. So what is in here? Like the main thing is the GBT tuning challenge, the gradient booster Asian tree tuning challenges. What challenges we have like GBT models like XG boost or light GBM and CAT boost are powerful and win many Kaggle competitions. That is thing what has happened in the forums. The next is what is the main problem in this? Their performance is highly sensitive to hyperparameters. Throwing a model into production with default settings leaves massive performance on the table. So we should be very careful when we use this particular thing because with the training thing we cannot directly with the default settings, we cannot directly go for the production environment implementation. We have to do a hyper tuning, or it is very sensitive to the hyperparameters. The main point in using this is training a single GBDT model can be expensive because it uses large data and many trees are there, and running a full grid search over a complex spaces computationally prohibitive because it uses a very huge amount of space, huge amount of processing time, GPUs, and it also involves cost. Uh, so the question is, what we have to limit if we have a limited budget, say 50 training runs, how do we get the best possible model within the budget? So we are going to look into that, the Bayesian optimization for GBDT. So using the Bayesian optimization, we are going to optimize the model GBDT, Bayesian tree model. In this, like what are the methods we use here, how it works for GBDT, and why it's inefficient for GBDT, like manual search, educated guesses based on intuitions, docs, or something like that, and why it's inefficient because it is reproducible, slow, and expert dependent. So grid searches tries every combination in a predefined grid. It is a curse of dimensionality. Agility has a 10 plus important hyperparameters. A grid with just 5 values for each is 5 cap 10, that is greater than 10 million combinations, which is impossible here. And next is random search, randomly samples from the search space, better than grid search, but it has no memory. It might sample many similar poor performing points and based evaluations. Will occur. The Bayesian optimizations uses a surrogate model to intelligently guess the next best hyperparameters to try. So this is a Bayesian optimization. Why it is we see it is a winner of the among the other models. Like it uses past results to model the performance landscape. So it has a memory to utilize the past performances data which will be fed into the model to fine tune the model, focusing expensive GBDT training runs on the most promising regions of the hyperparameter space. It maximizes performance per dollar. It is a compute dollar. So it is something like we can say the budget friendly model, defining the battlefield, like what we have to do, like GBDT hyperparameter space. What it is, it is very crucial. Like such a BO depends on a well defined search spaces. Categorize the key hyperparameters like model complexity and the capacity. So, what is model complexity and capacity? These are the one among the categories. Categories the key hyperparameters. So, n estimator number of trees. More trees can learn more complex patterns, but risk overfitting. Search space example 50 to 1000 or something like that. Max depth, tree depth. Deeper trees can capture more interactions, but overfit severely. That is one thing. And num leaves light GPM specific, similar to max depth, controls complexity. Mean child weight, mean data in leaf prevents overfitting by requiring a minimum number of samples in a leaf. Learning rate and early stopping, like what is a learning rate, like ETA, like shrinks the contribution of each trees. This is the most important trade-off. Critical concepts or like learning rate and n estimators are deeply coupled, so both are coupled in this thing. And what happens is a lower learning rate requires a high n estimators to converge, but often leads to a better final model. So that is one advantage what we have here. And teaching tip, like that is you can ignore it. So randomness and regularization, subsample or bagging for fractions. A fraction of data to use for training each trees prevents overfitting. Call sample underscore by tree, or a feature fraction underscore fraction, like fracture of features to use for each tree. Reg underscore alpha L1 or reg underscore lambda. So regularization terms on the leaf weights, defining the search space in code. Example using Skykit optimization Python. So this is a code for the same. So the BUGB DT loop in action, like what it does, like step one is initialization thing, defines the objective functions. If of hyperparameters, validation scores, define the search space, choose an acquisition function or example expected improvement. And step one is initial design, the scouting party. The BO needs a few points to build its initial surrogate model. We use Latin hyper cube sampling, or a simple random search for 10 to 15 points to get a diverse static set. Step 2, the core loop for I in range n underscore trials. Build surrogate model. The BO library fits a Gaussian process GP to all hyperparameters or validation scores. Pairs collected so far, like maximize acquisition function, the system uses an optimizer to find the hyperparameter. There's x underscore next that look most promising according to the acquisition function. Example, the GP might be very uncertain about models with low learning rate and high n estimators. The EA function calculates that this region has a high potential payoff and suggests we try it. So next thing here is evaluate the true objective function, the expensive steps we call, because the system unpacks x underscore next into the GBDT classifiers. It trains the GBDT model on the training data, typically using cross validation, example fivefold CV to get a robust validation score. Crucial to save time, we use early stopping. We set a large n estimators, but still the trainer to stop it if the validation score hasn't improved for 50 rounds, and the actual number of trees used is a dynamic outcome. So that is one crucial thing about it. And next is update. What is this? The new x underscore next or CV underscore score pair is added to the history. The loop repeats. So this is how this true objective function there is happens. And visualization, like you can use this code or the following code to visualize the convergence plot and the search space plot. So in the convergence plot, the best validation score for score seen so far versus the trial number. It shows the rapid early improvement and then the plateau. What's the search space plot? Here, for two key params like learning rate and max depths, showing how BO samples densely in the optimal regions. Practical considerations and pro tips like choice of surrogate. Uh, Here use Optino, like Optino uses TPE, tree structured pairs and estimators, and the we call it the budget king, which is BO Bayesian optimization model. And worms.like can often worms.bo with a few known good hyperparameters changed from the documentation or real experiments to give it a head start. Next is parallelization. What is parallelization? Like running trials one by one is a slow process. So you run the trials parallelly with different data sets. Advanced BO libraries can propose a batch of points to evaluate in a parallel using techniques like penalizing points or close to each other in a hyperparameter spaces. So this is the core of like minimize the cross validation loss of an XGBoost model on the iris dataset. So here you import the libraries. The next is load data. Next one is define the search space, and next is define the objectives. So what it has, and run the Bayesian optimization. And once that is done, you will get the best results. So in the running the Bayesian optimization, so we run total number of evaluations, so 5 initial randoms plus 20 Bayesian optimization. And the final result of this is Bayesian, running the Bayesian optimization is we get an expected improvement value through the acquisition function. That leads the best results out of this. And so that's it for the. So tuning the GBDT, the gradient booster rotation tree model with the Bayesian optimization method. Next is moving on to the resume, the search process and recovering the search methods. So in this, So these are the real world problems we have in normal training things. When you are training a massive transformer models on your university or your own computer GPU cluster, you have 100 hours of compute budget. What happens when the hardware failure occurs after 72 hours? The power goes out. The scenario two is preemption. Your job gets killed because a higher priority research projects needs the GPUs. The next is scenario three, early insight. You notice good results after 20 trials and want to add more budget without starting over. Scenario four is model selection. You need to pause tuning to test the best so far model on a holdout set before deciding whether to continue or not. So you have to start from the scratch. It's computational wasteful, often impossible because it wastes a lot of resources, cost, money, and human resources, and the GPUs and the memories as well. So here we use the concept called what does resuming actually means. Key insight is resuming. It's just about the best hyperparameters found so far. It is about recovering the entire state of the optimization algorithm. It is something like what needs to be saved, the search state or something like that. The trial history, the complete log of all hyperparameters validation score pairs. This is the fundamental data set for any surrogate model. So next is the surrogate model. And in the circuit model for Bayesian optimization, the exact state of the Gaussian process, all kernel parameters, the covariance matrix condition on the observed data. For TPE Optina, the Poisson estimators for L of x by y and g of x by y. The analogy is something like you cannot just know where you have been on the map or something like that. You need to know the entire updated map itself. So that will give you what are the places you have already visited in the map. Optimizer state for the acquisition function. So random number generator states to ensure deterministic behavior, internal state of the LVFGS or other numerical optimizers used to maximize the acquisition function. The next is metadata, the search space, definition, timestamps, system information, the objective functions or a hash of it. Visually, like implementation patterns across frameworks. Uh, that is code focus. Like I'll just walk through the code. So call back-based checkpoints, SkyKit optimizations are used here. You can see like this resume logic. So how the resume function will work. And so we'll continue this resuming the search process and recovering the search methods. Uh, looking into this implementation patterns across frameworks. In this we were this thing is entirely about the resume logic, how to resume from where we left. That is discussed, like remaining calls 100 minus len checkpoint x iterations, or like checkpoint content x iterations, function values, etc. Whatever we perform. So here in the result, it will like GP underscore minimize objective space in number of calls equal to remaining calls. So those the information will be there in the resume functions. So we will be invoking those. So pattern two is database backed storage. So if we use a database backed storage, so the details everything will be loaded onto the database. So we have to do a study with the SQL, SQLite backend, and like we use the Optino here for better performance, and we load the database. So this is the location of the database. So next is the pattern, the custom checkpoint, the pointings like what we do. We have auto save results like where the history and file names will be there. So with that we'll be opening the file name and pickle them. We call this here like history from the history. What file needs to be loaded? That will be loaded here. So previous results, the file name will have the where it left details. So we will load the file name from the database. So in the main loop, we'll be using this previous results, load previous results, checkpoints. Uh, if previous results optimized and restore the previous results. So next is the mathematical implications of resuming. So what are the challenges we face on that? Like Bayesian optimization, the posterior where D is observation history is updated sequentially. So the posterior the observation details will be stored sequentially, so it will be easy for us to retrieve it. If D is exactly the same, the received GP will be mathematically identical to one that never stopped. So sometimes, if not much progress happened at the beginning or the start of that particular process, if it gets abandoned. So it will there will not be much changes you'll see. So it will start from the beginning. So we have to start working on that. The consistency of the randomness when you save or restore the uh, random state, the sequence of the proposed points is deterministic. Without this, the resumed search would explore a different random path, making results non-reproducible. The cold start versus warm start problem. The like what is cold start? Like beginning with random points. Warm start is the beginning with the either happens the full previous history to resume a few known good points from a previous experiment or something like that. The advanced topic and best practices we call. So what are those? So one is version control for ML. The next thing is files should be treated as experimental artifacts. Uh, they enable exact reproduction of the results. And space definition drift is the next one. Like so why we say it's warning? Like if you change the search space definition between resumes, the results may become invalid. Solution for this problem is a hash the space definition will be included in the checkpoint. So objective function drift is similarly if the objective function changes except for different data preprocessing, previous trials becomes incomparable distributed and parallel improvement is the next one. In this frameworks like Optina with SQL backend naturally handle multiple workers. For custom implementations, careful locking mechanisms are needed to prevent race conditions. So, to summarize from this topic, like why do we use the resume function? It is something like computational efficiency. So, like we discussed earlier, if it's the model is trained for 72 hours out of 100 hours, if it gets interrupted, then the resource utilized will be lost. Like if you have a budget constraint, then it will, the budget will be wasted. So for this, this racing function becomes an advantage to tackle those kind of problems. What to save, like complete a search state, trial history, plus surrogate model, plus optimizer state. So those things should be saved. And how to implement use framework callbacks, SK opt, or database backends Optina. The mathematical integrity and proper resumption maintains the statistical properties of the sequential optimization process, and these are the best practices. So, because for the best practices, we have to version tuning for search spaces and objective functions, especially in search settings and real world relevance. This skill is essential for large scale models tuning in both academic research and industrial applications where compute resources are valuable and shared. So that's all about the